What if everything we've been told about gravity is only part of the story? We've all heard about Newton's falling apple and Einstein's curved space, but what if there's a deeper truth that flips everything we know on its head? In this mind-blowing journey, we dive into a revolutionary theory that says gravity isn't a force at all. It's motion. Pure, simple, elegant motion. Space and time aren't just the backdrop, they're the main event. And they might just hold the key to unlocking the universe itself. Get ready to rethink physics, challenge the status quo, and discover the cosmic dance that could change science forever. The Gravitational Enigma. Gravity, it's the silent force holding our universe together. From falling apples to orbiting planets, it governs everything. Yet, beneath its familiar face lies one of the deepest mysteries in all of physics. More than 300 years ago, Isaac Newton formulated the laws that let us calculate gravity's effects with astonishing precision. But he never claimed to understand why it works. He described what gravity does, not what it is. That mystery was left for future minds to solve. Enter Einstein. In the early 20th century, he reshaped our view of the cosmos. His general theory of relativity replaced gravity with the curvature of spacetime. To many, it was revolutionary. But even Einstein admitted his theory didn't explain the origin of gravity, it simply reframed it. And he asked us not to look too closely at the assumptions beneath it. Today, some of the most respected physicists, Dicke, Bondi, de Broglie, Heisenberg, still question whether we truly understand gravity at all. Their consensus? General relativity, though elegant, is incomplete. Its predictions are subtle, its tests few, and its progress since 1929 nearly stagnant. Despite the acclaim, Einstein's theory hasn't led to the deeper understanding science usually demands. It hasn't unlocked new insights or connected meaningfully with other fields. In fact, some argue it has reached a dead end. So here we are, centuries of brilliant minds, oceans of data, and gravity remains an enigma. Perhaps, as this text argues, we've accepted too much on faith. Maybe it's time to challenge our assumptions. Maybe it's time to look beyond Newton, and even beyond Einstein, for the truth hiding in the unseen fabric of reality. A new vision of gravity. In the last chapter, we were left with a question that's haunted science for centuries: what is gravity, really? Now, we step into the bold territory of answers. The heart of this new theory begins with a radical idea: space and time themselves are not fixed backgrounds, but ever-progressing entities. Just as we experience time flowing forward, space too, in this view, expands outward from every point in all directions, continuously and uniformly. Imagine spacetime not as a stage, but as a moving current. Everything in the universe, even without motion of its own, is swept along by this cosmic flow. This is more than metaphor. It's a foundational postulate: each location in spacetime moves outward from all others at the speed of light. As a result, objects that appear stationary, like photons right after they're emitted, still move outward because of this progression. Their motion isn't their own, it's spacetime carrying them. And we see this in nature. Photons, for example, fly away from their source at light speed in all directions, not because they choose to, but because spacetime itself is unfolding beneath them. Even distant galaxies move away from us faster the farther they are, a behavior perfectly consistent with this continuous expansion of spacetime. In this model, the redshift and recession we observe aren't due to galaxies hurtling through space but rather spacetime itself stretching out. But here's where things get truly profound. Opposing this universal outward motion is a second, inherent movement within matter itself. Every atom, this theory suggests, contains a rotational motion in spacetime, directed inward, counter to the outward flow. When nearby, this inward gravitational motion overpowers the outward progression, pulling matter together. At greater distances, the universal expansion wins, pushing objects apart. This elegant push-pull dynamic explains not only the attraction we associate with gravity but also why, at cosmic distances, galaxies recede from each other. It's not a contradiction, it's balance. And there's more. This theory provides an answer to one of astronomy's long-standing puzzles: why are stars spaced so far apart? Based on the balance point between spacetime progression and gravitational pull, there's a natural limit to how close two massive bodies can come together unless already bound. For stars, this limit is around 2 light-years, precisely what we observe. Not due to chance or chaos, but due to fundamental physics. Globular clusters, densely packed star systems, once baffled scientists. They hold together tightly but don't collapse. Why not? In this model, stars in these clusters remain just outside each other's gravitational limits. The cluster as a whole pulls them inward, but their individual positions maintain a perfect equilibrium. No need for rotational forces or mysterious dark components. Even more powerfully, this new view of gravity breaks free from the old dilemma: is gravity a force that acts at a distance or something transmitted through a medium like curved space? This theory says, neither. There's no need for invisible messengers or distorted geometry. Instead, gravity is simply the result of matter's inherent motion within the structure of progressing spacetime. There's no pulling at a distance, just objects following their natural motion paths. No delay. No medium. Just motion. Einstein famously equated gravity to acceleration. This theory goes further: gravity is motion, not just equivalent to it. It doesn't need a gravitational field to transmit effects. The actions of masses are independent, yet they create the illusion of interaction. Much like watching debris from an explosion, if played in reverse, it appears as though particles are drawn together, even though each is simply tracing its own path. And here's the stunning twist: all of this works without adding complexity. No extra fields. No patched-in forces. The same two postulates, the outward flow of spacetime and the inward motion of matter, explain gravitational attraction, the structure of star clusters, the redshift of galaxies, and the minimum spacing of stars. It's a unified, minimalist framework with maximum explanatory power. By redefining gravity as motion, rather than force, this theory removes the need for mystical assumptions. It bypasses Einstein's semantic tricks, avoids the murky realm of action at a distance, and clears away the fog left by previous models. What we're left with is startling in its simplicity. Matter moves inward. Spacetime moves outward. Gravitation is the result of this cosmic choreography. And still, this is only the beginning. Part 2 delivers what the author calls a second-order explanation. The deepest question, what causes this gravitational motion within matter, is still to be answered. That's where Part 3 comes in, promising to reveal the atomic-level origins of gravity and complete the picture. But already, this new view reshapes our understanding. Not as a mere alternative to Newton or Einstein, but as a theory that explains what they could not. It doesn't rewrite science from scratch, it refines it, resolves contradictions, and connects phenomena once thought unrelated. A universe not pulled by invisible hands, but carried along by the tides of space and time themselves. The hidden harmony of gravity. What if gravity isn't a force at all? What if the mysterious attraction we've observed since Newton's apple fell from a tree is not something acting between objects, but something emerging from the very nature of space and time itself? Welcome to Part 3 of Beyond Newton, where we leave behind centuries of assumptions and step into a bold, all-encompassing theory that redefines the universe from the ground up. This is where gravity stops being a puzzle and becomes a natural consequence of deeper principles that might be simpler than we ever imagined. The theory is called the Reciprocal System, and it begins with a strikingly elegant idea that space and time are not only connected, they are exact reciprocals. For every unit of space, there's a corresponding unit of time. Not metaphorically. Not geometrically. But literally. They are two expressions of a single entity, spacetime, existing in discrete, quantized units, each possessing three dimensions and governed by the simplest mathematics, Euclidean geometry and ordinary arithmetic. This may sound abstract, but from it flows a vision of reality that explains everything from the motion of galaxies to the cohesion of atoms. Let's break it down. We begin with the idea that spacetime is constantly progressing. Every point in spacetime is moving outward from every other point, uniformly and without preference, at the speed of light. This is not a background expansion like the old models of the universe suggested. It's a built-in, ever-present progression, a kind of cosmic heartbeat. So if every location in spacetime is moving outward, what happens to things that don't have any independent motion, things like photons, fresh out of a light source? They move outward too, not because they're pushed, but because spacetime itself carries them forward. The constant expansion of spacetime explains why radiation spreads, why photons travel at light speed, and why distant galaxies seem to recede faster the farther they are. But here's the twist: not all matter follows the outward flow. Some things move against it. Matter, what we call atoms, built from rotating photons, possesses an inherent inward motion, a kind of built-in resistance to the expansion. It doesn't need to be explained as a force. It's just the nature of matter to resist the outward pull of spacetime. This inward motion, balanced against the universal outward progression, is what we call gravity. Think about that. Gravity isn't a force pulling things together. It's a motion built into the fabric of matter, moving in the opposite direction of spacetime's outward flow. Two simple motions, spacetime pushing out, matter pulling in, explain everything we've observed in the universe. And it gets better. At small distances, this inward motion dominates. That's why stars hold together. That's why planets orbit and apples fall. But at cosmic scales, where the outward push has more room to act, it wins. That's why galaxies race away from each other. There's a natural gravitational limit where the inward motion of matter is exactly balanced by the outward motion of spacetime. Inside this limit, gravity rules. Outside it, expansion takes over. This model explains why stars are spaced so far apart, about 2 light-years. It explains why globular clusters, those dense collections of stars, don't collapse under their own weight. The outward motion of spacetime balances the inward motion of each individual star, holding the cluster in perfect equilibrium. But what about down at the atomic level? Traditional physics has struggled to explain why atoms don't collapse. Forces of attraction, gravity, electromagnetism, would suggest they should. Yet they don't. Why? Because this theory introduces a brilliant twist: gravity reverses at the unit level. At distances smaller than 1 unit of space, gravity becomes repulsive. That's right, in this model, gravity pushes atoms apart when they're too close, just as it pulls them together when they're far. It's not a contradiction. It's a natural result of the spacetime ratio moving away from unity, outward above it, inward below it. That shift is what creates stable atoms, resilient solids, and liquid cohesion. Even more impressively, the reciprocal system requires no additional assumptions. It derives all this from just 2 postulates. 1. The universe is made of spacetime, discrete, 3-dimensional, and reciprocal. 2. It follows normal mathematics and geometry, no warping, no exotic variables. From this, it predicts everything we observe: gravity, radiation, matter, cohesion, even the shape of time itself. Speaking of time, this theory doesn't treat time as a mere ticking clock. It treats time as a 3-dimensional structure, just like space. What we usually call time, what clocks measure, is only one component, clock time. But time also has coordinate dimensions, much like space. And when we move at high speeds or encounter extreme gravity, we're tapping into this deeper structure of time. That's why Einstein's relativity gets results. It noticed the effects, even if it misunderstood the cause. The reciprocal system reveals that there's no need to bend space or stretch time. The effects of high velocity or gravity on time come naturally from its hidden dimensions, not from deforming reality. It brings common sense back into physics, no need for rubber rulers or magic. Even better, this system predicts behaviors Einstein's relativity can't explain, like the exact spacing of stars, the stability of globular clusters, and the internal cohesion of solids. It even aligns with the famous Michelson-Morley experiment, by showing that light's constant speed is a consequence of spacetime progression, not a paradox. And it does all of this without redefining measurements or inventing fields. It simply treats space and time as equally real, equally dimensional, and mutually reciprocal. Most astonishingly, the motion of matter, the cohesion of atoms, and gravity itself all turn out to be different expressions of the same underlying motion, a rotation against the flow of spacetime. This isn't just a gravity theory. It's a complete physical system. A theory that doesn't stop at particles or planets, but reaches across scales to unify the cosmos. So what does this mean for science? It means we may no longer need to rely on theories that require arbitrary adjustments or exotic additions like dark matter or extra dimensions. Instead, with 2 simple postulates and a single reciprocal relationship, we gain a model that aligns with everything we see and makes powerful predictions about what we haven't yet understood. In short, Beyond Newton doesn't just extend the laws of physics. It reimagines them. It transforms gravity from an invisible force into a natural motion. It turns time from a mystery into a mirror of space. And it transforms our picture of the universe from fragmented forces into a unified dance of reciprocal motions. No equations, no ether, no guesswork. Just motion. Simple, beautiful, and universal. Challenging relativity, the rise of a new understanding. The history of theoretical physics, wrote Sir James Jeans, is a record of dressing accurate mathematics in flawed interpretations. And nowhere is that more true than with Einstein's theory of relativity. In this final part of Beyond Newton, we confront a towering figure in modern science, not to tear down Einstein's work, but to illuminate its limitations and introduce a bold alternative, the reciprocal system. Unlike past theories, this system doesn't require theoretical gymnastics or evasive postulates. It begins with clarity and ends in coherence. So what's the issue with relativity? At its core, Einstein's special theory of relativity tries to reconcile the constant speed of light with the way we measure motion. To do this, it makes a daring move. It denies the existence of absolute motion. According to relativity, there's no such thing as a universal frame of reference, everything is relative. But this bold step is more about avoiding contradictions than revealing physical truth. Einstein's first postulate says motion is purely relative. But it doesn't explain how or why, it just sidesteps a contradiction. It's like a courtroom rule preventing a witness from testifying, not because they're wrong, but because their testimony could be inconvenient. Einstein's solution allowed for mathematical consistency, but not necessarily physical understanding. In contrast, the reciprocal system accepts absolute motion, but redefines what that means. It suggests that every object moves relative to the actual framework of the universe, the complete spatial structure defined by the motions of galaxies, once you correct for their recession and random movements. Within this absolute system, motion can be measured, and the contradictions of relativity dissolve. Let's talk about Einstein's second key idea, that mass increases with velocity. At high speeds, particles don't accelerate as much as expected. Einstein interpreted this as an increase in mass. And indeed, countless experiments with particle accelerators seem to confirm this. But as many physicists, including de Broglie and Bridgman, have admitted, that's only one way to explain the data. The reciprocal system offers another. It says mass remains constant, but force decreases at high speeds. Why? Because force is not a thing acting on mass, it's simply a way of describing motion. As an object approaches the speed of light, the difference in velocity between the object and the effective spacetime progression shrinks, so the effective force weakens. Acceleration slows not because mass grows, but because there's less room for additional motion. This explanation requires no imaginary mass increase. It preserves logic. And it aligns perfectly with observed behavior, without needing ad hoc assumptions. Now consider another iconic success of relativity, the equation E equals mc squared. Both relativity and the reciprocal system agree on the math, but not on the meaning. Einstein said mass is energy. But the reciprocal system argues that mass and energy are different states of spacetime displacement, one three-dimensional, mass, the other one-dimensional, energy. They're not the same thing, they're convertible forms. When mass turns into energy, like in a nuclear reaction, one vanishes, the other appears. They're not simultaneously present, as Einstein's interpretation suggests. Then there's the famous precession of Mercury. The planet's orbit shifts slightly each cycle, beyond what Newtonian gravity can explain. Relativity accounts for this with warped spacetime. The reciprocal system offers a different path. It shows how coordinate time, a missing piece in classical physics, adds extra motion at high velocities. Mercury's high speed means it experiences this effect strongly, hence the shift. Throughout all these examples, the pattern is clear. Einstein's theory is brilliant but fragile, built on clever workarounds and assumptions that can't always be tested. The reciprocal system, in contrast, arrives at the same results, or better, through simpler, more logical foundations. What about general relativity? This extension of the special theory tries to deal with non-uniform motion, acceleration and gravity. Its famous concept, the equivalence of gravitational and inertial mass, is something the reciprocal system not only agrees with, it strengthens. In this model, gravity is motion, specifically, an inherent inward movement of matter in opposition to the outward flow of spacetime. No need for curved space or coordinate transformations. General relativity also claims that laws of physics must hold in all reference frames, a concept known as covariance. But as critics like Bridgman pointed out, this requirement is largely mathematical theater. Any law, no matter how wrong, can be made to look correct under the right transformations. It's not a test of truth, it's a test of form. And while Einstein's equations are often praised for their elegance, they're notoriously complex and abstract. As H. Bondi admitted, they're nearly impossible to apply beyond simple situations. The reciprocal system. It's built from ordinary geometry and simple math, yet it unlocks profound insights across physics. In fact, this system not only matches relativity where it succeeds, it extends far beyond it. It explains the expansion of the universe, the spacing of stars, the structure of atoms, and even the cohesion of solids, all from the same foundational principles. It eliminates the need for imaginary constructs like space curvature or variable mass and never uses evasive tactics to escape contradictions. Most importantly, it passes the ultimate test of a scientific theory. It matches observation not just occasionally, but consistently, and across vastly different scales and fields. In the end, Einstein's theory filled a void in physics, a necessary step forward in its time. But it's not the final step. The reciprocal system shows us that it's possible to retain the insights of relativity while shedding its contradictions. It restores clarity to physics. It brings us back to logic, back to geometry, and back to motion, not mystery. Einstein gave us a language. But now, we finally have something to say. Rewriting reality, the final word on gravity, time, and the future of physics. What if the paradoxes that have haunted modern physics for over a century aren't signs of nature's mystery, but clues to a conceptual error we've overlooked? In this final installment of Beyond Newton, we arrive at a grand and radical conclusion. The reciprocal system of theory, a framework built on two simple postulates, has rewritten our understanding of space, time, gravity, and motion. It offers not just clearer explanations, but a complete shift in how we think about the structure of the universe. Let's start with time. Most of us think of time as something clocks measure. But clocks don't track time in its totality, they track just the progression of time, one of two crucial components. The other component, called coordinate time, has been almost entirely overlooked by conventional physics. And this oversight, the reciprocal system shows, is the root of many of the contradictions in Einstein's relativity. Clocks measure motion in time, a consistent progression that exists for all matter. But just as we recognize random motion in space, like the erratic drift of galaxies, there's also random motion in time. At low velocities, this coordinate time is negligible. But at high speeds, close to the speed of light, it becomes significant. This is the real source of relativistic effects, and understanding it helps us dismantle some of the most infamous paradoxes in science. Take the twin paradox. According to Einstein's theory, one twin flies off in a spaceship at near light speed, returns, and finds his earthbound brother aged decades. But that logic assumes time slows down for one twin simply because of his motion. The reciprocal system shows the flaw here. Biological aging and clock behavior are local processes, determined by local physical conditions, not by abstract reference frames. Time doesn't stretch or shrink because you're moving. It behaves normally, everywhere. A related puzzle is the clock paradox. Two clocks separate and rejoin after one undergoes acceleration. Relativity says the moving clock ticks slower. But if all motion is relative, who's to say which clock moved? The entire scenario becomes absurd, and many physicists simply brush this aside with pages of dense math. But as the reciprocal system reveals, the problem isn't in the math, it's in the assumptions. Einstein's approach relies heavily on denying the existence of absolute motion. But this denial causes contradictions that keep cropping up, again and again. What's more, even relativists themselves accidentally reintroduce absolute motion, often referring to movement relative to the fixed stars, which is really just a euphemism for a universal frame of reference. Why not just admit it? The universe itself provides an absolute reference. We're surrounded by cosmic indicators, stars, galaxies, the cosmic background. Motion relative to this grand structure is not only meaningful, it's measurable. The reciprocal system acknowledges this and builds a theory where motion, force, and time all have real, physical meaning. Now let's dig deeper into the concept of force. In conventional physics, force is a cause, something that pushes or pulls. But in the reciprocal system, force is simply motion. There's no magical mechanism at play, just matter following its natural path through a progressing spacetime continuum. That's why the whole concept of a gravitational field collapses under scrutiny. Einstein insisted gravity was a distortion of space caused by mass. But to make that model work, physicists had to reintroduce something suspiciously like the ether, a medium that was supposedly discarded in earlier theory. In truth, they didn't eliminate the ether, they just renamed it curved space and gave it all the same magical properties. Here's the bottom line: there is no field. There is no need for a gravitational medium. Objects aren't pulled across space by invisible hands, they are in motion because of intrinsic spacetime dynamics. This is why galaxies appear to repel each other, or why debris flies outward from an explosion. The interactions are not mutual. Each object follows its own independent trajectory, shaped by the fundamental push-pull relationship between space and time. What about Newton's law of gravitation? Hasn't it been proven wrong at high velocities? Not at all. The reciprocal system shows that Newton's equation is exact, and deviations, like Mercury's orbital precession, come not from gravity, but from misinterpreted time behavior at high speeds. Once coordinate time is properly accounted for, the numbers match precisely. Einstein's curved space isn't needed. Neither is a propagation delay for gravity. Gravity, like all motion in this system, is instantaneous, not because it breaks the speed of light, but because it's not transmitted. It's an internal property of matter. Now consider another foundational aspect: simultaneity. According to Einstein, two distant events cannot happen at the same time because we can't measure them simultaneously from a distance. But this, again, confuses total time with clock time. In the reciprocal system, simultaneity means events occurring at the same stage of the progression. And yes, this can be known, defined, and measured. This redefinition of time leads to profound insights about space. Space, like time, is not a passive stage. It's in constant motion, progressing outward in all directions from every point. This progression is scalar, meaning it moves equally outward from each point in 3 dimensions. That's why galaxies recede from us in every direction. It's not that they're flying away, it's that space itself is expanding, and matter, with its inward-directed motion, appears to cluster or orbit based on this balance. This dual motion explains everything from star spacing to cosmic expansion, without inventing dark matter, dark energy, or inflation. There's no need to fudge the math or invent unseen forces. It all flows naturally from 2 simple postulates. Let's revisit those now. 1. The physical universe is composed of space and time, existing in discrete units, with 3 dimensions each. 2. The universe operates under the rules of ordinary mathematics and Euclidean geometry. That's it. From here, the reciprocal system derives radiation, matter, gravitation, cohesion, inertia, and even the structure of the atom. It answers questions the standard model can't even properly phrase, without invoking fields, curvature, or tensor equations. It also critiques the modern obsession with mathematical complexity. Physicists today seem to believe that if a theory isn't wrapped in dense symbols and multidimensional abstractions, it can't be serious. But the reciprocal system reminds us of something Newton never forgot: simplicity is power. You don't need tensors to describe gravity. Newton's equation, yes, that humble, centuries-old formula, remains the most accurate, practical, and universal expression of gravitational behavior we have. And now we know why it works, because it's not an approximation. It's a reflection of the way motion truly functions in a reciprocal spacetime universe. In the end, Einstein's greatest flaw was not his math, it was his refusal to let go of faulty concepts. When his theory hit a wall, he introduced new abstractions rather than admit foundational errors. The reciprocal system takes the opposite path. It strips away complexity and exposes the simple, elegant mechanisms behind nature's most mysterious phenomena. And that's the true power of this work. It doesn't just fix gravity, it transforms physics into something intuitive again. It revives the dream of understanding the universe, not through endless variables, but through deep, conceptual clarity. Time is motion. Gravity is motion. The universe is motion. And now, finally, we can understand that motion with the kind of elegant simplicity Newton once imagined, but couldn't yet explain.